Imagine trying to recognize someone's emotions from their brainwaves, but you've never seen their brain patterns before. This is the core challenge of cross-subject EEG emotion recognition, where massive individual differences create distribution shifts that break traditional models. Let's first understand why this problem is so difficult. Building on this challenge, we're dealing with a domain generalization scenario where each person's brain represents a different domain. The authors tackle this using 62-channel EEG data with differential entropy features across 5 frequency bands. This comparison highlights the key insight. Instead of treating the brain as a uniform structure, the authors leverage functional brain regions backed by neuroscience. They also move beyond single constraint approaches to collaborative domain generalization. Now let's dive into how their region-aware spatiotemporal modeling with collaborative domain generalization actually works. The framework flows through these 4 stages, each addressing a specific aspect of the cross-subject challenge. The subject alignment provides initial calibration while the region-aware module captures spatial brain organization. The region-aware module is particularly clever because it prevents non-physiological cross-region connections. The dual-branch design captures both stable region-level patterns and discriminative sparse couplings within each functional area. The temporal transformer brilliantly addresses the multi-scale nature of emotion dynamics. While emotions have immediate neural responses captured by local attention, they also have longer-term patterns that the global encoder identifies through periodic sampling. The collaborative approach is what makes this framework truly powerful. Instead of relying on a single alignment strategy, they jointly optimize multiple complementary constraints that address different aspects of domain shift. Let's examine how this framework performs across multiple emotion recognition benchmarks. The evaluation spans 3 progressively challenging datasets with increasing numbers of emotion classes. The Leave One Subject Out protocol ensures truly unseen test subjects, making this a rigorous domain generalization test. These results demonstrate consistent superiority across all datasets. What's particularly impressive is that the improvements hold even as the task becomes more challenging with additional emotion classes. The confusion matrices reveal interesting patterns in the model's behavior. Notice the strong diagonal elements indicating good overall classification, with particularly robust performance on sad and positive emotions. The off-diagonal confusion tends to occur between emotionally similar states, which actually aligns with psychological understanding of emotion spaces. Let's understand which components drive these impressive results through ablation analysis. The ablation studies reveal that collaborative domain generalization provides the biggest performance boost, with distribution alignment being the most crucial constraint. This confirms that addressing subject variability through multiple complementary losses is the key innovation. The interpretability analysis provides confidence that the model learns meaningful patterns rather than spurious correlations. The attention maps align with known neuroscience findings about emotion processing in frontal and temporal regions. Every breakthrough comes with challenges that point toward future research directions. The main limitation is computational overhead during training, attributed to the multiple gradient computations required for collaborative optimization. The authors also note challenges with interclass balance that affect practical deployment. Future work focuses on making the approach more practical through efficiency improvements and better handling of class imbalance. Extending to mobile EEG devices could enable real-world emotion recognition applications. Let's consider the broader implications of this work for neurotechnology and brain-computer interfaces. This work opens possibilities for plug-and-play emotion recognition systems that work immediately for new users. The neuroscience-grounded approach also demonstrates how domain knowledge can enhance machine learning for neural signals. This research shows how thoughtfully combining neuroscience priors with advanced machine learning can tackle fundamental challenges in brain signal analysis. The collaborative domain generalization approach represents a significant step toward practical, subject-independent emotion recognition systems. You can explore more cutting-edge research like this at emergentmind.com to stay at the forefront of AI and neurotechnology.